This video will demonstrate how to create calibrated images using the Mica toolbox. I'll start with a simple example showing how to calibrate this raw image I have that's simply taken with a standard camera. First, I will go to the Mica toolbox and generate multispectral image. This will bring up lots of different options, and here I'll go through what these options mean. So first, the camera type. The toolbox supports visible and UV, and if you have pretty much any other camera configuration, so a camera that's sensitive to visible, infrared, ultraviolet, however many you want, you can create your own calibration file that will mean the toolbox can support your camera. This is just a simple human visible color image, so I'll just select visible here. The type of image is a raw photo. The toolbox supports lots of different types of input images. For example, if you take an unknown image off the internet and have no idea how to linearize it, it's just a JPEG, then you could, for example, use this sRGB profile. In practice, I've never found any image which actually conforms to the published sRGB standard. It's very rare that the camera would match the dynamic range of the published standard. So I would essentially never recommend using this unless you know almost nothing about your image. You can also create your own custom nonlinear linearization model. So use this if you're using, for example, a JPEG image taken by a smartphone or a still frame that's taken from video footage. You can create your own linearization function. There's detailed instructions on how to do that on the website. So you can, if it's a JPEG, you can select that. Linear image, this is a very rare example where you might already have a linear TIFF image that you wish to use in the toolbox. So there's options for that as well, but very few people will have anything like that. And the recommended format for use in the multispectral image calibration workflow is a raw photo. And raw photos are excellent because raw images preserve the information straight from the sensor. And sensors behave linearly with respect to the amount of light hitting them. So twice as much light hitting the sensor will register a pixel value that's twice as high. So no linearization is required, and we can extract the nice linear values from a raw photo. Next, you can specify whether the standards are in the same photo or a separate photo. Ideally, the standards should always be in the same photo, but in practice, let's imagine you're taking a picture of an animal. You might take that picture but not be able to get the standard next to it because it's a wild animal. So then you might take the photo without changing any of the settings, very quickly go and put the grey standard where the animal was and take another photo of that standard in the same position using the same camera settings and with identical illumination. Then you can use a separate photo to calibrate the first photo. It's called the sequential method sometimes. There's this option to estimate black point. So cameras try to work out where black is. The camera sensor will always register some amount of noise even when part of the image is completely black. And many cameras will try and estimate this, for example, by shutting the shutter on the camera and measuring the dark current through the sensor. But sometimes there's reasons why the camera isn't able to do that, because, for example, the black point is being confused by lens flare, which the camera can't really do anything about. Or if you're photographing on a slightly misty day or through turbid water, and you don't have two standards, you can have this estimate the black point, which effectively looks for the darkest pixel in the image and assumes that is black. And that's a big assumption, so this needs to be used with care. If you have a case where you might not know the black point, where the camera might not be able to work out where exactly black is, so what number refers to 0, it's best to use 2 or more standards. And here we can specify the reflectance standards in the image. So every image should have at least one reflectance standard, and here you can input the values of the standard or the standards. In this example, I have 2 standards. I have a 7% standard, so I'll put 7, and a 93% standard, so I'll put 93. Just separate the 2 by a comma. You can have any number of standards here, though in practice there's not much point having more than two, unless you really need two standards. It's very rare that you actually require two standards. Normally a single standard is sufficient, but in this example I'll use two. If you know that your standards aren't perfectly grey, and you know what deviation from grey they have, you can use this option. So when we're selecting a standard here, this assumes that the grey standard has exactly 7% reflectance across the entire spectrum that the camera is sensitive to. In practice, that's a bit of an assumption. Even the best standards in the world don't have uniform reflectance across their grey levels. So if you know that you have a very different standard, or for example you're using a colourful standard, you might have a series of images where you don't have a perfect grey in the image, but there was always a colourful object in the image. You could potentially use that to calibrate your images. So here, if you click this, it will bring up options to specify your own standard levels. The standards move between photos. You only need to click this if you're photographing in visible and UV or even more channels, and the standards move following alignment. The standards move between photos. If you're choosing a visible and ultraviolet or more, so the image requires alignment between multiple pictures, you can specify how that alignment should be done, whether it's automatic or manual. And here the output, so you can choose lots of different types of output. I'll go into a bit more detail with these later and show you the different results that you get. If in doubt, choose linear normalized reflectance stack. This will show you a grayscale stack with all of the layers shown. Next, you can specify the image name. This is a really useful point at which you can specify the name of your sample and any treatments that are in the image. Because the name here will be preserved throughout all of the data processing steps later on. And finally, you can also specify whether the raw files or the image files should be renamed along with the image name here, which is very useful if you have a folder that's full of hundreds of raw files. It lets you know that which image files have been already turned into calibrated images. So when we're ready, I'll just click OK. I'll find this example picture. And so here we have the picture. It's being shown to us as a nonlinear color image, and it's asking me to select the 7% standard. So I just draw a box over the 7% standard, click OK, and then it's asking for the 93%, click OK. So that's it. It's loaded a calibrated normalized reflectance image. Here you can see I can move between the slices. So this is a grayscale stack with the visible red normalized, green and blue. The log window shows you lots of different options which have changed slightly since the Micro Toolbox version 1. So we have additional options. For example, we can easily measure the mean value. So if I just press M on my keyboard, let me select the white standard, for example. If I press M, it will just measure the mean values of the area I've selected. And remember, these should be 93, and they look very close to 93 because that's the reflectance of the grey standard. Now I'll select the 7% standard and press M. And here you can see it's measuring almost exactly 7%. And I can now very easily measure, for example, parts of the butterfly, just measuring them with the objective camera vision normalized reflectance. The numbers here in these calibrated images are now also in percentage reflectance relative to the standard values. Previously the values were on a 16-bit scale, which confused a lot of people. So now you can see these numbers are all on simple reflectance values, which should make things a lot less confusing. Now I'll demonstrate how to load up the image again and the different viewing options. So I'll once we've made a multispectral image, if we go back to the folder where the raw file is, here you can see the raw file has been renamed with the name of the label that we've given it, and this mspec file, this is the information specifying how to turn this raw image into a calibrated file. This is actually a simple text file, and all of these numbers tell the toolbox how to load up this image and how to load up the calibrated image. So now I can reload this mspec file that I've just made, and here we've got different options for viewing the image. So I can just select a linear normalized reflectance stack, so that's the default, and if you want to convert the image into cone catch values, this is the one that you should always choose. You can also load the image as a linear stack, so it doesn't perform the normalization step, which lets you just look at the raw values in the image. This is very rarely going to be useful, and it is particularly it will be of use if you're interested in measuring something about the illuminant itself, so without performing the normalization. Normally we want to perform normalization to remove the color of the illuminant, but sometimes you might not want to do that for various reasons. Linear color image, I'll show what this loads. So this effectively loads exactly the same image, but it shows it to you in color instead of a grayscale stack. So this is a linear color image. We can measure it. It's linear and normalized. So if we measure one of these standards, press M, you can see it. The values are objective reflectance values. But you'll also see that linear images are really, really dark. That's a standard property of linear images. We perceive brightness on something like a log scale. So once something looks linear, it looks quite odd to us on a screen that's designed to show nonlinear images. So it's very difficult to actually see what's going on. You can make out the different details in the butterfly. The color definitely helps over the grayscale image if we wanted to select regions, but it's still quite difficult to see some of the darker parts. For example, the dark part of the butterfly versus the gray background is very difficult to distinguish. So if we wanted to select regions, for example, cut out the butterfly from its background, this is still quite a difficult image to use. So I'll show you another option, which is to load a nonlinear image. So I'll select the same image again, and now I'll select nonlinear color image. So here is exactly the same image again, but now it's being shown to us as a nonlinear color image. And now you'll see it's very easy to distinguish the dark wing from its background. This image has actually simply been square root transformed. So if we were to measure parts of it, and if we square these numbers, we would actually get reflectance values. But because this has been made non-linear, caution should be used when measuring any values from this image. But now it's very easy to select different parts of the image because we can see them much more easily. So let's use some of the functions of the toolbox where we can specify regions of interest. So I'll just very crudely show how that can work. I can select an area of the forewing here, for example, and if I press F on my keyboard, it will create a region of interest labeled F1. And here, if we look at the ROI manager, it's created this region of interest here. Now I can select another one, and I'll press F again for forewing, and you'll see it's labeled it F2. The log shows all of the keyboard shortcuts available for different functions. So some functions have been reserved for example, M for measuring, R for measuring ROIs, S for the scale bar, E for eggs, and 0 for saving. But all of the other letters can be used to specify different regions of the image. So for example, now I can choose an area of the hindwing, and I'll press H for hindwing, and H for the other hindwing. Here you'll see the 4 different regions of interest that we've created. Many different functions in the toolbox, for example the QCPA framework, require a scale bar to be used. So when we're using a scale bar, we can just select it at this stage, draw a line anywhere in the image that you know the distance of. So I know that this is a distance of 30 millimeters. Just draw the line and press S, which brings up this dialog, and type in the length of the scale bar. I'll type in 30 here for 30 millimeters, and that means that throughout the entire toolbox and the framework I'll be using the millimeter to specify lengths. So that's added the scale bar. So now we have our regions of interest and the scale bar. We can press 0, this is really important, press 0 on your keyboard, and that saves the ROIs with the multispectral image. You'll see the log now says ROIs saved, and if we go back to the folder where we have the multispectral image, here we have the mspec. This zip specifies the ROIs, that's the ROIs we've just saved, and here is the raw file. So we can just close the image now, we can close everything down, and if we want we can now reload the image. Let's say linear normalized reflectance stack. And the image has automatically been loaded up again with all of its regions of interest. And now we can, for example, use R on the keyboard. If I press R, it will automatically measure the reflectance of the different patches that I've selected. So here we have the mean and standard deviation of red, mean and standard deviation of green and blue, etc. And it's labeled them based on the image label, and F1 for forwarding 1, F2, etc. Now we can also convert this image into a cone catch image. So at the moment the image is in camera visual space, as it were. So it's the camera's red, green and blue output. And every camera will differ slightly in its sensitivity to red, green and blue. So in order to convert this into animal vision, make it objective, we need to convert this image into a cone catch. So to do that, first you need to have created a cone catch model for your camera, and you can do that either by knowing something about the spectral sensitivities of the camera or by using a color chart, and you'll find guides on the website showing you how to create these models. So to convert to cone catch, I can just go convert to cone catch here and select the visual system that I want to use. Here I'll use the example of converting to CIE XYZ based on behavioral data from humans, which is a standard way of modeling colors for human visual space. And this is a model I've created for the camera system that I've used. And you can tick here to remove negative values. It's quite useful. If you tick this, it will highlight where the negative values are. Negative values can imply that some parts of the image are beyond the color gamut. They can't be recreated either by the camera or the visual system, or there's been a slight problem with the linearization. So it's handy to tick that. So here it's converted the image to XYZ. So this is human XYZ sensitivities, which roughly correspond to red, green and blue. And this is a stack, so X and then Y and Z. So again, I can press R on my keyboard to measure all of these different ROIs that we've selected earlier. And so if I press R, it will provide measurements of X, Y and Z. Also, specific to the CIE XYZ space, it's often more useful to convert this into CIE LAB space. And there's a simple tool provider to do that, so we can go image transform XYZ to CIE LAB. And here we have the CIE LAB space, so here's L, which is the luminance channel, A, which is the red-green component, and B, which is the blue-yellow component. So it splits the image into luminance plus 2 color opponent channels. And again, I can press R on my keyboard to measure the L, A, and B components of each of the ROIs that I've selected. Image exposure is a really important thing when creating calibrated images. If an image is overexposed, any parts of the image that are overexposed have reached the saturation point of the sensor, so the sensor can't go above its maximum value, and it effectively cuts off any pixel values above that, and it can create very misleading results. So an image with overexposed parts cannot be used. Likewise, if an image is underexposed, it creates a lot of extra noise in the image, and particularly with the confusion around where exactly the black point is, this noise can introduce systematic problems. So I'll demonstrate creating a multispectral image where there is some overexposure in the image, using all the same settings. So now it's showing me the image and it's asking me to select the standards. And you'll notice parts of the image that are overexposed are being shown in this dark red pixel value. So the red shows that this image is overexposed in the red channel. If it were dark blue, then it would be overexposed in the blue channel. There are other parts of the image, not just the standard, that are overexposed. But importantly, because this standard is overexposed, we can't use it for calibrating this image. The grey standard, the 7% standard here, though, is absolutely fine. So we would be able to use the grey standard alone for calibrating this image. And importantly, you'll actually see the butterfly. There's no part of the butterfly that's overexposed. So this image is actually very well exposed. The only parts that are overexposed is the white standard. So I'll press escape now. And if we did want to use that image, I would just use the 7% standard on its own, keeping all the other variables the same. Now select the 7% standard, and that's it. So here we have the butterfly nice and well exposed. The white standard here is going to give meaningless values. So if I measure the grey standard, press M, these values are all nice, around 7, but if I measure the white standard, you'll see it gives meaningful results in the green and blue channels, but not for the red. That's far too low to be trustworthy. You can see here it's a block of color that's all the same values, whereas in the green and blue it seems to be working fine. So this highlights the danger of using overexposed white standards, but thankfully the toolbox highlights when there's likely to be overexposure. It's often quite difficult to know exactly which photos to use, and exposure bracketing is a really good strategy when taking your calibrated images to make sure you have a range of photographs of a different level of exposure in the hope that you'll have at least one picture which is of a perfect exposure. The problem with that is that you end up with lots of images, and it's sometimes difficult to know exactly which ones to use. Another feature of the toolbox is how easy it is to use ultraviolet and visible images together for calibrating across to the cone catches of animals which have ultraviolet sensitivity. So here I have an example of a folder where I have a series of photographs taken in visible and ultraviolet, and I used exposure bracketing, so I don't know which is the optimal exposure to use. So I can use the screening function, the photo screening function of the toolbox, to work out which is best. So now I'll select visible and UV. When using the screening function, it supports a very wide range of raw images from different camera manufacturers. So for example, Nikon and Sony, etc. So if you have your own raw file which has a different extension, you can just add that to the list here and it will load any images in the folder which have these extensions. Again, you can specify whether to estimate black point. You can specify your standards. As we've seen before, it's the white standard is sometimes overexposed and is much brighter than the rest of the image, so it probably doesn't make sense to always use the white standard. A photo which is exposed in a way that makes the white standard well exposed will actually probably be underexposed for some of the picture parts that we're measuring. So I'll just use the 7% standard here, and you can specify the preview size of the photos here. Choose a size that fits your monitor. Now I'll just need to select the folder here that contains all of the raw images. And it will go through each image in turn, loading it and demonstrating how well exposed it is. The histogram at the top here shows raw exposure levels, and the images here have been converted into non-linear colors to make them easier to see by using a square root transform. So between the two, it makes it easy to work out which bits of the image are overexposed and which images to choose when creating a calibrated multispectral image. Okay, so that's finished, showing you some of the functions here. And this is a photo screening stack, so we can go through. You can use your scroll wheel on your mouse, or you can drag this thing on the bottom, or you can use the left and right arrow keys on your keyboard to move between slices. So here we have the female Danaus butterfly. And this is the first picture, which seems a bit underexposed, but there's no areas of overexposure. You see all of the histogram values are clustered on the left here. This is even worse, even more underexposed. And here we have that last image, which is the white standard is overexposed, but all of the butterfly looks well exposed, and the grey standard looks good. So this looks like a good visible image to use. So in this case, I'll select this as the visible photo. And I'll highlight the 7% standard and click measure. Next, I'll need to find the ultraviolet. If you're not using an ultraviolet image, now you can just the option to create the mspec comes up here, and you can just create that. But now I need to select the ultraviolet image, so I'll select the best exposed one. And here are the three. So this first one looks quite good. None of the images, the pixels are overexposed in the butterfly. Only the white standard is overexposed. This looks underexposed, and this is just verging on overexposed. You can see some of the pixels here, and the bright parts of the wing are overexposed. So I'll use this first one where there are no parts of the image overexposed. So I'll select this UV photo, and I've already highlighted the 7% standard. Now I just need to click this to create an mspec image. So next we've got options for alignment. So you can either choose no alignment if you think you have a perfect alignment, or automatic alignment, which will try and do it automatically, or manual alignment, which I'll demonstrate now. These scaling loops and step size are options just for the automatic alignment. Custom alignment zone lets you specify which region of the image to use for alignment when using the automatic or manual. And then we have the same options for output image type, so whether it's a linear, normalized reflectance stack, or all of the other options. And we'll give this a label here and rename the raw files. So it's asking to draw a box over the area to use for alignment. Now it brings up this manual alignment image, so we can zoom in and we want to drag one part of the image over the other until the alignment is perfect. So I just drag and release until I have a nice alignment. If I need to rescale the image, I can also use these plus and minus values. So if you had to refocus because your lens is not particularly good at working across the visible and UV range, Sometimes you might need to refocus. Refocusing changes the zoom very slightly, so you'll find it beneficial to rescale the ultraviolet to make it match the visible. Once you're happy with the alignment, you can just click Accept. And here it's created a calibrated multispectral image across the visible and ultraviolet channels of the camera. So here's the visible red, visible green and visible blue, and then the ultraviolet blue and ultraviolet red. So going deeper and deeper into ultraviolet. So now we can convert this image to cone catch if we wanted. So I'll use the example of a blue tit. And I can go convert to cone catch and select the model that I've already made, the blue tit model for this camera. And we have no negative pixels, so that's nice. And here we can see we have a cone catch image where we have the blue tit long wave, medium wave, short wave, ultraviolet and double cone channels. If we wanted to make a presentation image of this, that's quite easy to do. This is a tetrachromatic image, so there's no standard way of presenting the colors of a tetrachromat to us human trichromats. So there are lots of different options we can use. I'll just demonstrate one example. So to convert this stack, this cone catch stack, into a nice color image, I can use the image visualization and make presentation image function, and here we can specify which channels to output as red, green and blue. So I'll demonstrate here first using the blue tit long, medium and short wave as red, green and blue. This is a cone catch image, and cone catch images are on a range of 0 to 1, so a 100% reflectance should be converted to a cone catch of 1, and black is 0. So it's already detected that the maximum should be 1. And here you can specify the degree of non-linearity. This uses a simple power transform to create a non-linear image. If you have a number of 1 here, the image is linear, and linear images are very dark. If you have a value of 0.5, that's equal to a square root, which is quite extreme non-linearity in the image when combined with the gamma curves of standard displays. So a power of something like 0.7 to 0.8 produces nice results, but you can change that to whatever you want. Optionally, you can convert to RGB color if you want. Without converting to RGB color, it outputs a 32-bit image. But you can still save it as an RGB image if you want. So here it's created a nice color image of the butterfly. So this is in blue tit, long, medium and short wave in place of red, green and blue. The white standard looks a bit odd because remember it was overexposed. So the white standard is giving slightly misleading color results here. The grey standard, though, you'll see the one that we used is absolutely fine. Next, we can also output a UV version of this image. So for a tetrachromat, we need to present the ultraviolet somehow, and there are lots of different ways of doing this. Let's make a presentation image. And one way of doing it is to present ultraviolet relative to shortwave. So here we can specify shortwave as being yellow and ultraviolet as being blue. And this will create an image which highlights the differences between shortwave and ultraviolet, which is often quite an easy way of seeing which parts of the image are interesting in ultraviolet. So here we go. So between these two images, these are showing us all of the colors present, and there's really not that much interesting going on in ultraviolet with this example. But now we can look at the more interesting version in ultraviolet, which is this the male of the same species. Let's reset this. The photo screening tool. Reset this and select the male. So this photograph of the male looks well exposed, at least for the grey standard and parts of the image we're interested in. So I'll select this as the visible image. And in ultraviolet you can see these areas of the wings are very highly UV reflective, and this looks a little bit overexposed. You can see there's some parts of overexposure going on here, so I think this is probably the best image to use in ultraviolet. Select that, and I'll select the same results here, same options here. Specify this as the male. Specify the area to use for alignment. So you can see actually this spec here, that should be aligned on top of that one. And this looks like a good alignment. Okay, and now I'll convert it to blue-tit cone catch again. And we do start to have some negative pixels now, so that implies that these are in dark areas of the image, so it's probably just because of sensor noise that these are going into negative values, so that doesn't look like it's anything to worry about. And here we can see this is the ultraviolet channel for the blue-tit, and it's really powerful in ultraviolet but not nearly as powerful in shortwave. So here, if we create a false color image to highlight this ultraviolet, image visualization, make presentation image, I'll have shortwave versus ultraviolet here. Now any parts of the image that are blue are highly UV reflective, whilst also not being shortwave reflective. So here you can see that this butterfly wing, the iridescence here, is really, really highly UV reflective. So that's it. This video has demonstrated the two main ways in which it's possible to create calibrated multispectral images using the Micro Toolbox, and you'll find a wealth more information on the details of doing this on the website.